Good afternoon, everyone. Let's begin with today's lecture. The topic for today's lecture is engineering materials, and in this lecture we are going to talk about metallic materials, how we classify different types of metallic materials. We will have also a review of phase diagrams and also the phase diagram for iron and carbon, which you already had it in materials and manufacturing 1 unit. However, we are going to have it reviewed again because a good understanding of the phase diagram is required in order to be able to follow some of the lectures in this unit. And we will do a number of problems in the third session of the phase diagrams as well. So it will help us refresh our memories with whatever we have already learned in materials and manufacturing 1 unit on the phase diagrams. Then we talk about different types of ferrous metals as well as the method of production of iron and also steel. Well, first of all, let's talk a little bit about metallic materials. In the previous lecture, it was mentioned that we make use of different types of engineering materials, including metallic materials and some other engineering materials, including ceramics, polymers, and also composites. Perhaps it is fair to say that metallic materials or metals are the most important group of engineering materials. Why is this? Why can we call metallic materials as the most important group of engineering materials? There is a list of some reasons why we call them the most important type of metallic materials. As we can see in this slide here, metallic materials generally have a set of properties. A set of properties that satisfy a wide range of applications. We can find some type of metallic materials that are extremely hard, in a way that they can be used as cutting tools in order to cut other metallic materials, other metals, and even non-metals. At the same time, we can find some metallic materials that are extremely soft, very soft compared to steels and other types of materials. Soft and also ductile. Not just that. We can find some metallic materials that are conductive, very conductive to electricity and also heat, which is not the case for non-metals. And also, when it comes to manufacturing, in manufacturing processes, what we do is to receive a raw material in a given shape and size. And in order to convert it into a useful product, what do we need to do? We will need to subject it to deformation by making use of different manufacturing processes, including machining and other metal forming operations. And because many of the metallic materials are ductile, they can be easily subjected to deformation, such as forging and rolling and some other metalworking operations. And also we can subject them to machining and remove materials from them. This is not possible or not easily possible in the case of non-metallic materials. And eventually we can say that engineers understand metals. What is meant by this? Let's take a look at our own knowledge. If we want to list the properties of different types of metallic material, different types of engineering materials, that includes metallic materials and non-metallic materials, for which one we can actually provide a better description of the properties. Say, for example, compare what we know of metallic materials in terms of their properties with ceramics. We know a lot more about metallic materials. Reason we make use of metallic materials in almost every product that is made. The body of the car, for example. So many other things that we use in our everyday life. Metallic materials are used in order to make them, and we all know that metallic materials are known for a set of properties that are quite familiar to us. And this is explained to some extent in the next slide, in this one. Why metallic materials are important. Here we can see a list of some properties of metallic materials. They're very well-known properties. Those are high stiffness and strength. We know that metallic materials are very stiff. And also they are very strong. And this is one of the reasons why metallic materials are used in order to say form the main structure of buildings and superstructures in many cases. They are very strong. And they are very stiff as well. When it comes to toughness, what is meant by toughness? Do we know what toughness means?
How hard is the material, the capacity to absorb energy, like the hardness of the material?
Yeah, you can say so. You can say so. When it comes to fracture, a material that is tougher will show a higher resistance to fracture. And this is defined as toughness. And compared to ceramic materials, for example, metallic materials are very tough, making them suitable for certain applications, of course. Well, electrical conductivity and also thermal conductivity. If we are after a material which is highly conductive, of course we will go for metallic materials and we forget about ceramics and polymers. And also cost. We can say that, it's safe to say that metallic materials are less expensive than the other types of materials. Reason, they can be easily produced and they can be easily processed, making them quite convenient and suitable for certain applications when it comes to the cost of material. Any other properties that we can add to this list? Who's going to help us in order to add some other properties of metallic materials that are known to us and are not listed here? Anything else you can add to this list? Ductile, they are ductile, and this also provides us with convenience of manufacturing. If we want to change the shape of the material, then if we are dealing with a ductile material, it's quite possible and convenient. Yeah, that's a good one. What else?
Magnetism.
What's that?
Some metals are magnetic, and sometimes in construction it's good to have materials that are magnetic.
That is correct. That is correct. Yes, this is also another important property which is quite useful for some certain application. We have got some magnetic metallic materials. Okay, what else? Well,
malleability and ductility.
Malleability, more or less it's the same as ductility, which is right. But anyway, it's a different name of the same, indeed, property. Yeah. And also, what else?
Conductivity, the ability to control power, like
Yeah.
electricity to conduct.
We've got it here. We are after the ones that are not listed here. Appearance, they look nice. For example, the body of the car. Why is it made of metallic material? Because it's quite smooth, strong at the same time, and it is convenient to be used in order to make the body of the car, the panels and that sort of stuff. Suppose that if we don't have a metallic material available and we want to make the body of the car making use of another type of material, ceramics would not be a good choice because they have got high density and they are brittle as well at the same time. If we go for polymers, how about polymers? Can we make use of polymers in order to make a car, the body of the car I mean? We may, but it will not be as desirable as metallic material. It will not be as strong as metallic material, of course. And when it comes to, say, resistance to heat, in hot days of summer, maybe the color and also the shape will change. However, we can make use of composite materials in order to produce the body of the car, and in some certain types of cars, the body of the car is made of composite material. Okay, let's move on. Metallic materials, when we want to make use of metallic materials in order to produce different products, are available in different shapes, the ones that are listed here. Cast metal is a very common type of production of raw materials, raw metallic materials. We cast them into different shapes, and and it forms the general shape of the product, and then we subject it to further processes in order to bring it to the final shape and geometry. And wrought metal is another method of production of metallic materials, that is, material has been subjected to some sort of hammering, such as the forging operation. We've got the billet of the material which is subjected to hammering, then it comes to in a specific shape and size, and it may require further operations in order to be brought to the final shape and geometry. And also powder metallurgy. What is it? We had that in the previous lecture. What is powder metallurgy? To have the material, raw material, in the shape of powder, and then it will be subjected to pressure and also elevated temperature that is referred to as sintering. And after this, it will take final shape and geometry. These are typical types of starting forms of metallic materials that are made available to us. And of course, we can add some more to this list as well. These are the most common methods of forms of starting raw material when it comes to metallic materials. And how do we classify metallic materials? The broad classification is listed here. We divide them into ferrous and non-ferrous metallic materials. And which one is of common use? Of the two types that are listed here, ferrous and non-ferrous, 75% of the tonnage of metallic materials goes to ferrous metals. And they are the ones that are based on iron, of course. And non-ferrous refers to all other types of metallic materials, pure metals and alloys of aluminum, titanium, silver, copper, and so many other types of materials. And what is meant by superalloys? Some special alloys that are produced in order to be used at certain working conditions, where in a situation where temperature is high. So if we make use of a typical metallic material, it will not last for a long time. We've got to make it in a way that it can maintain its properties, its hardness, its stability at elevated temperature. In order to make this happen, we've got to make use of certain types of alloys in the material to make the material last at elevated temperature. And in some environments, when the possibility of oxidation is really high, we've got to make use of superalloys in order to make the product last long. And this is made possible by addition of high quantities of alloys to the alloying elements in order to improve certain properties of metallic materials. Well, what is meant by alloys? Addition of different types of elements to one another will result in production of alloys. In most cases, we make use of alloys rather than pure metallic materials. For example, we have got pure gold, pure silver, and pure copper. But they may not provide us with set of properties that we are interested in. For example, let's talk about silver. Pure silver is very conductive to electricity. Very conductive to electricity. However, what puts a limit on the range of applications of silver is its strength. Correct. It is very soft. It is very soft. And when it is very soft, we cannot make use of it for certain applications. If we add 7.5% of copper to pure silver, what happens? We add 7.5%, only 7.5% of copper to silver.
It becomes an alloy, but it's stronger.
Correct.
Because of the properties of copper and the conductivity of silver.
Exactly. Then what happens is that we will increase the strength of silver, of pure silver, significantly, making it suitable for so many applications, which wasn't possible when silver was just in the form of pure silver. And when you add 7.5% of copper to silver, it is called sterling silver. That is very strong, and it is still highly conductive. Of course, when we are adding another element like copper, which by itself is a conductive metallic material, the conductivity of silver will be sacrificed, but not much, just a little bit. And it is worthy of adding this much of silver to it in order to improve its strength significantly. And because of this, we are often after certain properties in any type of metallic material. And those properties may not be necessarily available in any type of metallic materials. So for enhancing the properties of metallic materials, we've got to mix them with one another in order to produce alloys. And alloys are commonly used in different types of materials and for certain applications. Well, in this slide we can see that alloys are divided into two main categories. What are they? Solid solution and intermediate phase. What is meant by a solid solution? Recalling from materials and manufacturing 1 unit. What is meant by a solid solution? You've got it up here. An alloy in which the elements of these are the elements. An alloy where the one element is dissolved in the other one in a way that a single phase still is in place. What do we mean by this? Well, it appears that having a little issue to bring the laser pointer on. Take a look at this image here. As you can see, in this region, what we have got is a single phase that is referred to as phase A. We have got atoms of two participating elements, element A and element B, or metal A, metal B. But the number of solid atoms is in a way that still the main crystal structure is in place and it doesn't change. As long as the crystal structure is the crystal structure of the base metal, we are dealing with a solid solution. There are some impurity atoms in it, however, properties are still a function of the crystal structure, and this is actually say the crystal structure of the base metal. So this is the dominant crystal structure, and this will affect the resultant properties significantly, despite the fact that solid atoms will change the properties to some extent. However, as the number of solid atoms increase in the base metal, what happens? Then it reaches to a limit, it exceeds the solubility limit, and then as a result, a second phase, that is phase B, is formed within the first phase. And something like what we have got here will be formed. That is, we have a matrix of the first phase, that is phase A. Within the first phase, we've got some islands or colonies of the second phase. And if you take a look at it, you can notice that the crystal structure of this island or this region is different from that of the base metal. And why is this? Because the number of solid atoms in this region is greater than the other regions, and this will affect the crystal structure of the product. And in this case, we are having an intermediate phase, and this has resulted because of exceeding the solubility limit, so that all the solid atoms cannot be dissolved within the matrix of the first element. And what is the result of this? If we have got an intermediate phase in place, how does it affect the properties of the alloy? Will it be any different from the one that we had in phase A only?
Does it create what is called like a fracture boundary, or it creates spots where the molecules line up so it's easy for fractures to occur?
Exactly. First of all, in this region, the composition of the material is different. The composition is different. Why is this? Because we are having a larger number of solid atoms in the material. So the composition of this region or this island will be different from the other positions in the phase metal. And because of this, the resultant properties will be different. Not just that, even the crystalline structure is different. When crystalline structure is different, what is meant by this? Say, for example, if you are having BCC crystalline structure in this region, and we are having FCC crystalline structure in this region, then the number of slip planes and slip systems will be different in different regions. And we know from Materials and Manufacturing 1 unit that some certain properties of the metallic materials is a function of the number of slip systems present in the given crystal structure. Right? The number of slip systems in FCC and BCC are different. And because of that, ductility of the material will change. So we end up with a material with intermediate phase when in some certain positions it is more ductile, in other regions it is less ductile. So it will affect the overall properties of the material if this happens. Okay, and this is a phase diagram we are familiar with, eutectic alloy. Do we recall anything from Materials and Manufacturing 1 about this type of phase diagrams? Yes? Yes or no? Yes. We do. We had this in Materials and Manufacturing 1, right? Towards the end of the semester, I would say. Okay. And then, what is meant by eutectic alloy? What is meant by the word eutectic? Let's put it this way. The word eutectic, as it's written down here, it means something. What is meant by eutectic? Easily melted. Indeed, it is derived from the Greek word eutectus, and it means easily melted. And why do we call this type of phase diagrams easily melted then, or eutectic? What's the reason behind this? Recalling from Materials and Manufacturing 1 unit, there is a certain composition right here. You can see it here at this point. Look, we've got the liquid phase up here. Where is it where we can have only liquid phase at the lowest temperature? Right this point. This is all liquid above this line. In this region, in these triangular regions, we have two phases present at the same time. It's solid and liquid. But anywhere above this line, that is the liquidus line, we have only a single phase, and that is liquid. So only at this certain point, this point, we can have only a single phase, and that is liquid, and that is at the lowest temperature possible to have a single liquid phase. And this is referred to as liquid point, as eutectic point, and this composition is referred to as eutectic composition, right? Okay, why is it called easily melted? If we want to melt this material, for this certain composition, that is 61.9, you heat it up all the way. What you have got down here, this is solid use, of course. Below solid use, you can have only solid. So all the way you have only a single phase, and that is solid, all the way up to this point. At this point, as temperature goes above this point, you will have again another single phase, and that is only liquid. And we never face a region or a temperature where we have two different phases present at the same time. So it's either liquid or it is solid. However, if composition is anything other than this, moving this way or the other, if we elevate temperature, say for example for a composition of 80% of tin, you elevate temperature, goes up to this point, is still solid. In this region, we will have a temperature range for which we will have two different phases existing at the same time, liquid and solid. And above this, we will have only liquid. Same applies to this composition, 40% tin. All the way up solid and liquid, and above this only liquid. And only for the composition of eutectic, that is 61.9, we will have either solid or liquid. And we'll never face a temperature range for which we will have solid and liquid present at the same time. So why is it called easily melted then? If you want to melt it, it's all the way solid up to this point. Beyond this, it's always liquid. Indeed, it behaves like a pure metal. What do we mean? Let's take a look at this end, this extremity where we have got 100% of lead. At this point we have solid all the way up, it's still solid, up to this point, that is the melting point for lead. You increase the temperature. What will you get up here? Liquid. So we will have either solid or liquid. Let's move on to the other extremity. Tin. It's always solid, up to this point, that is the melting point for tin. Above this, it is liquid. So, a eutectic composition is the only composition for which material behaves like a pure metal, despite the fact that it is not, it is an alloy. But it behaves like a pure metal, and it's always easier to work with pure metals because there is a certain melting point. At that given point, it melts. Below it, it's solid. Above it, it's liquid. So a eutectic composition always behaves like a pure metal, and this is a good property of material when it comes to melting and casting, for casting operations. We want to heat it up, melt it, and then put it into the cavity in order to make a product out of it. And always eutectic composition is the best composition for this type of applications. I'm not saying that if we are making use of non-eutectic composition, you cannot do the casting on this type of material. You can, but eutectic is the best candidate for this type of operations. Because when we are dealing with two-phase regions, we will have some issues, segregation and non-uniformity of composition on the grains. As you move from the center of the grain towards the surface, the composition will change. That is a phenomenon referred to as segregation. For eutectic composition, we never will have this issue. Okay. And what is this? Iron-carbon phase diagram. We had this before, right? In materials manufacturing 1. Okay. Just helping you to refresh your memory. In this phase diagram, we have the eutectic composition right here. But in this phase diagram, we have another similar point down here. And this is referred to as what? What composition is this? Similar to eutectic, it is the eutectoid composition. And this is, of course, liquids, and this is solid use, this one. Any material below this solid use line will be solid. So what is meant that material that is above this point and below this point, this is all solid. However, different types of solid material, which is not the case for eutectic. For eutectic, above this point we will have liquid, below this point we will have solid. For eutectoid, above and below both solid. Okay? And what else we need to know is that when it comes, first of all, let me ask you a question. Why is this phase diagram starting from 0% of carbon going all the way to 6.7 and not to 100? In the phase diagrams we used to have, the binary phase diagrams like the one that we had before, it has to start from, often it starts from 0% of one material, that is 0% of tin, going up to 100% tin. Now let's take a look at this one. It begins from 0% carbon, going all the way to 6.7, and not 100. Why is this?
All the interesting stuff is down that end.
What is it?
All the interesting stuff is down that end, the scale.
It's cut. This is the important part of this phase diagram. The rest of it isn't of importance for engineering applications. So there is no point of showing this. If we want to show this, we've got to go all the way to the next, I think, lecture theater to make it 100%. And it's only this bit which is of importance to us. So the importance will be lost. We have just a little section of it which is of use to us. So there is no point of showing it. The rest of it will have a lot of graphite in it. Graphite is brittle, it's useless, we don't use it, we don't show it. So it's only a section of it. Indeed, the right name for this phase diagram is not what we've got up here. It says iron and carbon. However, what we have got here is cementite on the other side, or iron carbide. Up here, we have got 100% of cementite. Indeed, 6.7% of carbon in this phase diagram is equivalent to 100% of cementite. And this can be referred to as iron and iron carbide phase diagram. That's a better name for this phase diagram. Okay? So, what we will have in this end is Fe3C, 100% of Fe3C at this end. That is equivalent to 6.7% of carbon. And to this end, of course, we will have iron, 100% of iron. Okay, and we know that for pure iron, within this temperature range, starting from the room temperature going up to 914 degrees C, what we have got is called ferrite, and the carbon content of ferrite could be up to 0.022% at this temperature, that is 727 degrees C. This is also referred to as eutectoid isotherm line. This line is referred to eutectoid isotherm line, and its temperature is this, 727. And at this point, we will have the maximum solubility of alpha ion to carbon, that is 0.022%. Going up above this point, that is 912. In this region, we will have a different type of ion. Its crystalline structure will change from BCC to FCC. And because of this, the properties of the material will also change, because crystalline structure has changed. Also temperature has changed, temperature range has changed. Anyway, we will have FCC all the way up to this point, 1394 degrees C. Above this, the crystalline structure will revert back to BCC. And the product is now called gamma ion, delta ion. That in this region, it's called gamma ion from 912 to 1394. And in this region, it is called or referred to as delta ion. And above this point, it melts. What is the melting temperature for pure iron? 1539. Okay? So this is the way it behaves. Pure iron is called an allotropic material, metallic material. What is meant by this? What is allotropy? it means that its crystalline structure will change at different temperatures. And this does not apply to all the metallic materials. Some of them behave just like this, and some other ones, they won't change the crystalline structure. And why this is? Well, this is still under investigation. There are some theories behind it, but nobody can actually provide an answer which is convincing everyone. However, we know that there are some certain types of materials that behave just like this. And these provides us with actually different solubility at this temperature. Take a look at this. This temperature is referred to as eutectic isotherm line. And that one, eutectoid isotherm line, of course. At this temperature, that is 1148 degrees C, we will have maximum solubility of iron to carbon. You can see that maximum solubility of iron to carbon at this temperature is this much. In that one, it's very small. But in austenite or gamma iron, maximum solubility is 2.14%, and it is huge compared to the other ones. And what is meant by this? It means that for this given type of material, at this temperature, we can accommodate a larger number of atoms of carbon in the crystalline structure of the base metal. A larger number, significantly larger number of atoms of carbon can be accommodated in void spaces of the atoms of iron. And this is used in heat treatment processes of steels. This is used in heat treatment processes of steels. As we can add more and more carbon to the steel, we make it harder and harder. So if you want to make it hard, it's better to elevate its temperature to this region so that you can add more and more carbon to it without formation of a second phase or intermediate phase. It is all solid and there is only a single crystal structure, and that is FCC or gamma. So there is a lot of carbon in it, and still a second phase is not formed. Then cool it down rapidly. So the atoms of carbon cannot move out of the crystal structure, and they are trapped where they are. And because of this, there will be a large content of carbon in the steel, and you can make them really hard. You've noticed how we make the steel hard. We put it in the furnace, right? And we quench it. So atoms of carbon diffuse inside of the crystal structure, and they are trapped wherever they are. But if this happens gradually, they may find the time in order to move out of the crystal structure and find right places for them in order to form some deposits of graphite, making it softer. So of this property, we can make use of this property in heat treatment processes. Okay. Any questions on this? Okay. Let's move on. This is what I just explained, so I'm going to skip this. The figures which I have included here may be slightly different from what we have in the textbook, because the textbook that we are using is not the one that is specifically to be used for materials engineering purposes. It's a general textbook for materials and manufacturing. However, if we do advanced materials and manufacturing unit, we will be making use of another textbook, and there are slight differences between the figures that are given for temperature ranges and also for carbon content of different products. I am making use of the ones that are more accurate, and those are the ones that will be used in another textbook. So in the slides, I have made all the necessary corrections. Whatever is in this slide is the one that is more accurate. Okay, hypoeutectoid steel and hypereutectoid steel. What is meant by this? Again, back to the phase diagram. If we are having a steel within this region with the carbon content starting from here going all the way to 0.76, if its carbon content is within this region, it is referred to as a hypoeutectoid steel. If the carbon content is above 0.76 up to this point, 2.14, then it is referred to as hypereutectoid steel. If its carbon content is exactly 0.76, then what is it called? Eutectoid steel. And this 2.14 is the maximum solubility of carbon in austenite. If carbon content is anything above this, more than 2.14, then we call the product cast iron. This is what we already know, right? Because it exceeds the maximum solubility limit of austenite. So any product which is produced in this region is referred to as cast irons. They are, of course, richer in carbon content, and this will affect the properties of the resulting material, of course. Well, and in this region, of course, if the carbon content of cast iron is exactly this much, 4.3, it is referred to as eutectic cast iron. If carbon content is within this region, starting from 2.14 to less than 4.3, then it is referred to as hypoeutectic cast iron. If it is more, what is it called then? Hypereutectic cast iron. Okay, good to know. And in this slide here, we can see classification of steels into 4 different categories, and those are plain carbon steels when the main participating elements are iron and also carbon, and there is no or very small amount of other elements like nickel, magnesium, chromium, and some other ones. We've got low alloy steels when the magnitude of the alloy elements cannot be ignored. However, it's not much. Of course, we have got some high alloy elements which are not listed here. These are the ones that are of common use. Low alloy steels in order to enhance some of the certain properties of the steels. For example, strength, resistance to wear, and some other types of property, resistance to corrosion. Stainless steels. What are stainless steels? They are known for a very important property. What is it? They are resistant to oxidation and corrosion. And why is this? Someone said something here. Chromium. How much chromium do we have in stainless steels?
I think it varies.
How much? Who is talking? Okay.
I'm not actually 100% certain. I think it's about, I think it's under 1%. But
At least 11%. Yes, correct. Thank you. At least 11% of chromium can be found in stainless steels. Could be more, 15% or even more. And why do we have so much of chromium in steel? 15% or 11% is a lot of chromium indeed in the steels. Why is this? Because chromium helps form an adhesive layer on the surface of the stainless steel. Very adhesive layer on the surface of the stainless steel. We can't see it, but it exists. And this adhesive layer protects it against the attack of atoms in the corrosive environment. Protects it and makes it really stainless and resistant against corrosion. And as there is more chromium, it will be more resistant, of course, to corrosion. And this is something that we'll discuss in advanced materials and manufacturing more. So presence of a lot of chromium will help form an adhesive layer on the surface of the stainless steel, protecting it in corrosive environments. And in many cases, stainless steels are also strong. Reason? Because of carbon content indeed. Carbon content will also increase its strength. Indeed, as there is higher carbon content in the material, it becomes more and more strong. And tool steels, what are they? The types of steels that are known for certain properties, and those are hardness, of course, very hard indeed. Tool steels must be very hard because they are the ones to be used in order to cut so many materials, including some types of steels, softer steels. And they have to be very good in terms of resistance to wear. And chromium also, and some other types of material, alloying elements are added in order to enhance this property of the material. And also they have got to be stiff as much as possible. For example, cast irons are very hard, but they are not very stiff. So if we make use of cast irons in order to cut other types of materials, they won't last long. They have got to be tough as well. Also in tool steels, we make use of quality steels, and also we make use of large amounts of alloying elements in order to enhance the properties of the material. By the way, it has to maintain its hardness. Tool steels need to maintain their hardness at elevated temperature. And tungsten and some other alloying elements are also added to enhance this property. Yes?
Structural steel sit in those categories?
Structure?
Where does structural steel sit in those 4 categories?
No, I don't think so.
No, where does it sit?
Where does it sit? Plain carbon steels. Or if there are some alloying elements in it, that will be low alloy steels. But most of the structural steels are the plain carbon ones, because you don't really need to enhance some certain properties that we listed here and we discussed here. So, by the way, plain carbon steels are the least expensive one. Least expensive ones of the ones that are listed here. And we don't make use of expensive steels for structures. Unless if it is really needed, then we go for low carbon steels, low alloy steels. Okay, let's take a look at this slide here. What is it telling us? Hardness and tensile strengths of steels are a function of what? Carbon content. Let's take a look at this. As we move from left to right, the carbon content increases. As carbon content increases, what is increasing? Hardness. What else? Tensile strengths. So they are both a function of carbon content, and this is what I just mentioned in the previous slide as well. And what is being sacrificed when this is happening? When we are adding more carbon to the steel, we are increasing its hardness and strength. Are we sacrificing something to make this happen? Yes, we are. What is it? Ductility. As a material becomes harder and harder, its ductility will go down and down further and further. So, indeed, we can say that hardness and the strength are inversely proportional with ductility. As one of them goes higher, the other one goes lower and lower. So, if we are having a very strong material, it's very hard to deform it, to bring it to a new shape. So, always keep in mind that we may need to achieve a trade-off between the properties that we are after. If we want a material to be deformed significantly, it's better to go for the one that has got a lower carbon content because it is more ductile and it is more deformable. If we are after the one that should be really strong, then it's the time for us to forget about ductility and go for the one with the with higher strength and less ductility. As I said before, a trade-off is often required between the different types of properties that can be found in different types of steels. And cast irons, as I said, the carbon content of cast irons is within this range, within 2.14, that's the maximum solubility of austenite to carbon, all the way up to 6.7, or to be more accurate, we can say 6.67% of carbon. Beyond this, at this point, we will have 100% of cementite, Fe3C. The other important element in it, what is it? The other important element, silicon. There is a lot of silicon in cast irons, 1 to 3%, depending on the type of the cast iron. We may find between 1% to 3% of silicon in different cast irons. Why is this? What is the role of silicon in cast irons? Well, what silicon does in cast iron is that when it is elevated, it is in the liquid form. We want to cool it down in order to solidify it, in order to make the products out of it in casting process or any other process. If there is no sufficient amount of silicon in it, what happens is that a lot of cementite will be formed in the product, and this is not good. We don't want that. And silicon prevents formation of cementite in the product. it dissolves it indeed into graphite. So there will be deposits of graphite present in, say, cast iron if there is sufficient amount of silicon in it. And that's what we are after. Because deposits of graphite plays some important role in the product. I'm not going to discuss this any further. This is something that will be discussed in Advanced Materials and Manufacturing Unit if we take it next semester. However, in, say, as we can see in this slide here as well, in cast irons, what we have got is iron plus carbon, and the other element which is present at really noticeable amount is this one, that is silicon. And as we can see here, in steels, we've got least amount of silicon and least amount of carbon, of course, up to 2.14. And just over 2% of silicon can be found in some certain types of steels. But when it comes to white cast iron, and particularly gray cast iron, we can find a larger amounts of silicon in it. And the reason, as I said, is that silicon does not allow formation of cementite. We want cementite to be present in steels because it is very hard and it increases the resistance to wear of the, say, steel. But we don't necessarily want large amounts of cementite in cast irons. Rather, we are interested in having some deposits and large amounts of carbon, graphite in it. That is indeed carbon. When they are concentrated in some certain regions, we call it graphite. Okay, any questions so far? Okay, now let's take a break for 10 minutes and then let's continue with what is left. There are some points that are listed in this slide here. Most steels have relatively low amounts of silicon. Why is this? In the steels we have lower amounts of silicon. Why is this? Because if there is a lot of silicon in it, it acts as a barrier against the formation of cementite, Fe3C, cementite. And cementite is a hard phase. And we want it in the steel. We want the steel to be strong. And it's desirable. It's desirable to have cementite in the steel, which is not the case, as I mentioned, in the cast irons. And because of this, there will be lower amounts of silicon in steel compared to the cast irons. And in this slide here, we can see two different types of cast irons. Those are white cast iron, and it has less amount of silicon and also carbon. And we've got gray cast iron with higher amounts of both of the elements that are silicon and carbon. Of course, this one is stronger than white cast iron in terms of hardness. And then there are some other types of say cast irons that can be produced from these two. For example, ductile cast iron. Ductile cast iron can be produced from gray cast iron by some special process, and this will be discussed in Advanced Materials and Manufacturing Unit as well. Similarly, malleable cast iron can be produced from the white cast iron by a certain process, and we will discuss it in Advanced Materials Unit if we take it next semester. Okay, and let's talk about iron and steel production. How do we produce iron and also steel? From iron ore. Western Australia is very rich in deposits of iron ore, right? So it's good to know how iron ore can be produced in order to produce steel and also iron from it. Before getting there, let's talk about different types of iron ore that exist in the nature. There are some certain types of iron ore in the nature. Have you ever seen a piece of iron ore? Any one of you? Anyone? Nobody. Okay, I have got some images right here. These are the images of some typical iron ores that can be found in the nature, as you can see. Often they've got a brownish color, like the ones that we can see here, starting from the top, going all the way. Or they are silver, the ones that we can see at the bottom two images. These are typical iron ores that you can find, say, in the nature, and these have got some certain amounts of iron in it. There are different types of iron ore. One of the famous ones is hematite, this one, Fe2O3, this one. It has got about 70% of iron in it. That's a lot. That's one of the really good ones. We've got magnetite, Fe3O4, and in this type of iron ore, often there is less than 70% of iron in it. However, there are instances where the amount of iron in the amount of, say, iron is up to 74%. Some other types of iron ores are siderite and also limonite. And as you can see, the chemical formula for each one of them are given in this slide here. Well, generally, we can say that iron ores contain between 50 to 70%. However, there are instances where you can see the amount of iron in it is less than 50% or even more than 70% in certain places. And then when we want to produce say steel and iron from it, we've got to make use of a number of other materials as well. Those include coke, limestone, and also hot gases, in addition to the iron ore or some scrap material, metallic materials that are to be recycled. In doing so, we've got to make use of a blast furnace. Have you heard of a blast furnace before? Well, it has got this structure as we can see here. A blast furnace is used in order to produce iron and also steel. Indeed, iron is produced in the form of, the product is called pig iron. Eventually, what is produced in the blast furnace will be subjected to additional processes in order to produce steels out of it. How it works, I'm going to play a video clip here that is showing us how a blast furnace is used in order to produce iron and also iron or pig iron from iron ore. And there is a useful video clip on YouTube that I'm going to play right now. Let's pay attention to this.
The 21st century, laced with state-of-the-art industries, majestic architectural wonders, rocket-fast automobiles, and enormous skyscrapers. It is hard to imagine our world without the magic of metal, without the magic of steel. So how has this wonder of super metal come into existence? And where does it really get made? The answer to this lies right here, beneath the ground and in the pits of fire. Steel, a hard, strong grey or bluish-grey alloy of iron with carbon, found in the very ores of our planet, along with other usual elements such as manganese, chromium, etc., is the most extensively used metal in our planet, having its origin from a very huge hot oven called as the blast furnace. The blast furnace, which gets its name from the method that is used to heat it, is a large steel structure lined with refractory fire bricks that can withstand temperatures approaching 2000 degrees Celsius. Although the origin of the blast furnace dates back to Han China in the 1st century BC, it was in 1709 that Abraham Darby developed a blast furnace that could be fired by coke instead of charcoal, which paved the way for modern-day blast furnace. Traditional blast furnaces are chimney-like structures which are actually 80 to 100 feet wide and 30 meters high, made of iron or steel and used chiefly in the process of smelting, that is deriving a metal out of an ore, in this case steel out of iron ore. The principle involved in this means of extracting metals is that of the reduction of the ores by the action of carbon monoxide, that is, the removal of oxygen from the metal oxide in order to obtain the metal. Lined with fire brick, the furnace is narrow at the top, increasing in diameter downward, but narrowing again suddenly almost at the bottom to form the hearth or crucible where the fine molten products are caught. The furnace is fed from the top, which has an entry referred to as the charging hole, with a charge of definite quantities of ore, coke and flux, consisting mostly of limestone, that is carried over the charging ramp. Water is then released, which travels through one end of the water channel and pours down from the other end, hitting the water wheel, which acts like a turbine. The water wheel starts rotating due to the pressure and the flow of water, causing the mechanism of cams to also move, eventually striking the tuyeres to bellow instantaneously. Thus, preheated compressed air is introduced at the bottom through tuyeres, entering just above the crucible. The air passes upward through the charge where coke is burned to form carbon dioxide and heat. The heat decomposes limestone into calcium oxide and additional carbon dioxide. Carbon dioxide oxidizes coke to form carbon monoxide at a high temperature of 1200 to 1300 degrees Celsius. The carbon monoxide then reduces the ore to iron, taking on oxygen and reverting to carbon dioxide. This gas, together with unused carbon monoxide, nitrogen and other constituents of the air originally introduced, is let off through a pipe from the top of the furnace, and being still at a high temperature is employed to heat the stoves into which fresh air for the process is brought. As the operation proceeds, the mass in the furnace becomes molten and descends into the crucible. The iron sinks to the bottom. Impurities called the slag, being lighter, float on the top. The slag is drained through a pipe in the upper portion of the crucible, which is called the slag pipe. The iron is tapped from below and is run into sand molds to harden. The product is known as pig iron or cast iron, and the place where it is hardened is referred to as pig iron bed. Thus, we now know the secret behind the origin of the miracle metal called steel that has practically shaped our civilization and way of life, from cars to cranes and bridges to buildings.
Okay, that was an interesting video clip, wasn't it? Yep. Anyway, that's the way we produce pig iron from the iron ore. However, let's take a look at the chemical equations of what was explained in the, say, video clip. If we have got the iron ore, which is this one, and the gas, carbon monoxide, then the first chemical reaction will take place, and by addition of coke, which is used in this process, the second chemical equation will take place, and eventually by addition of carbon monoxide and also iron oxide, we can produce, say, iron plus some dioxide gases, and this is the one that is of use in production of steel and cast iron. And all the three chemical equations were properly explained in the video clip, and it helps us in understanding how cast iron and also pig iron is indeed produced. Well, what is interesting is to know is listed here that for production of 1 ton of iron, we are in need of putting in place 7 tons of materials. That is 2 tons of iron ore, 1 ton of coke, half a ton of limestone, and 3.5 tons of gases are used in order to produce only 1 ton of iron, of pig iron. And once this is produced, the resultant material that is indeed pig iron is very rich in one element. What is it? Carbon. There is, as mentioned here, there is more than 4% of carbon present in typical pig iron that is produced. More than 4%. How much do we want to be there if we are going to produce steels? Maximum carbon content should be 2.14. And still, most of the commonly used steels have got carbon contents of much less than 2.14. Much less than that. Indeed, most of the commonly used steels have a carbon content of less than 1.4%. And what we have got is a pig iron which is very rich in carbon. We don't want that much of carbon in it. So we've got to get rid of the extra carbon somehow. And even for the case of cast irons, well, maybe we don't want that much of carbon in it, because anything above 2.14 will provide us with different types of cast iron. In order to do that, we are in need of subjecting, say, the pig iron to further processes. And those are to make use of BOF, that is basic oxygen furnace, as well as electric furnace, in order to produce steels from the pig iron. How it works? In the next slide, right here, we can see the structure of basic oxygen furnace, or BOF. As you can see, in this type of furnace, what we receive is the pig iron that is produced by making use of the blast furnace. What we receive is the pig iron with high carbon content. Then, as we can see it here, in this furnace, the pig iron is subjected to the flow of oxygen, pure oxygen, goes in, and then it absorbs the carbon from the surface of molten pig iron, as you can see it here, which results in formation of CO and eventually CO2. And this leaves the furnace in the form of a gas. So it takes some atoms of carbon with it. And this process continues for some time. As the process is in progress, the extra carbon is being removed from the pig iron, eventually reducing the carbon content to what we want. And if we are after certain types of steels, well, the carbon content has to be within certain limits. It has very accurate, then maybe we make use of some other types of furnaces, which I will explain later. In this slide here, we can see how BOF is used in order to say process the pig iron. This is the scrap material, whatever is to be recycled, which is actually charged in the furnace, and then pig iron is added. That is the molten pig iron, and eventually it is subjected to the flow of oxygen. And once extra carbon is removed, we can just tap it in another, say, chamber or cavity. And what is in this ladle, in the transfer line, is the iron, which significantly lower amount of carbon. So this is the one that is to be used for production of different types of steels and maybe cast irons. And if we want to add some alloying elements, this is the right place. Take a look at this. We are tapping pig iron, which is now processed with lower amount of, say, carbon. At the same time, because it is in the molten shape, we can add some additives, different types of alloying elements and whatever, in order to make different types of steels out of it. And the other furnace that is used is electric furnace. This is of course more expensive. Indeed, 70%, about 70% of steels are produced by making use of BOF. This is less expensive than the other method, and about 30%, as mentioned up here, about 30% of the steel in the US or in the industrial world, we can say that, is processed by making use of electrical arc furnace. And this process is more expensive than the previous one. However, this provides us with a better control over the carbon content of the steel that is produced. So, similarly, this type of furnace is used in order to lower the amount of carbon and also to bring the amount of carbon to the desired level for producing steels of higher grades, where the amount of carbon has to be at certain limits. Any questions so far? Okay. This brings our lecture to the end, today's lecture to the end, so I'm going to stop recording now, and then